Okay, let me just save the video here. So, oh, so many names. Right, the one we first, no, what was our first one here? This one that ended at, yeah, okay, no, yes. Yes. What was our first lesson? It was a lecture or tutorial? Lecture. Physics. Lecture. Electricity. Go away, yeah. Work and power. Oh no, I've twisted the I hate when this happens. It'll do. It does. Now you see, yeah. Okay, the next one was a tutorial on the same thing. Right now we're doing a lecture, and then previously was a lecture with physics, lecture, fields. This was for the other students. Current in a magnetic. Please. How did I do this? Amazing. Right. Okay, if you can write this down. The electromotive force and internal resistance. Come on. What? Good job. Yeah, you know this topic. It's your fave.
No, actually this one's not that bad.
No, it's not that. Not that bad. Right, continue.
Not as bad as capacitors.
You didn't think the capacitors we just did were that bad, did you?
I don't like capacitors.
Okay.
I like transformers, they're nice.
It is a good movie.
No.
Optimus Prime's my favourite.
Yeah.
Continuing. Right. So, potential difference, PD. Really, it's just another name for voltage. It's a more appropriate modern name for it. So, please note potential difference, meaning voltage. It's great. It's great. That's the best whatever it is ever. Okay, you know this word potential difference? Yes. No need to write it down? You sure?
I like a lot. I've been writing a lot recently.
Good.
All those working. There's another notebook as well.
Yeah, no, I heard of this, yeah. Alright, next. Now, electromotive force. So you could break the name down to get a meaning of it. What does the prefix electro mean?
Electricity.
Yes. Motive? Force? Force. It's a tricky one, that one. So, it's like the electrical motion force. In other words, it's that thing in the cell that makes the electrons move. Simple way of putting it. So you might say...
Is this the hand rule?
No, not yet. So in other words, the reason current leaves a battery, a cell, is because of an EMF, because the battery has an EMF. It has this sort of ability to push the electrons out. So this is coming from the fact that it has an EMF. And it's basically the voltage that you get from any source such as a battery. We think of it as the EMF. It's generally defined as the potential source in a circuit. In other words, it's where the energy is coming from. It's coming from the EMF. A device that supplies electrical energy is called an EMF. So again, I'm saying the same thing over and over again here. EMFs convert chemical or mechanical, but usually chemical energy into electrical. So you know a battery is a chemical, it converts chemical energy into electrical energy. The product of such device is also known as an EMF. So I think I've said EMF enough times in this. So what is the difference between EMF and PD? If EMF is a voltage and PD is a voltage, why do we have different words here? What is the difference between EMF and PD? Does anyone want to?
EMF is inside the cell.
True, but something a bit more basic than that.
PD requires 2 points. The measurement.
True, but EMF kind of does as well, the positive and negative ends of the battery, so it's something other than that.
Electromotive force is like the potential for electrons.
Stop getting too complicated. I said it's something simple, basic. So the difference is this: EMF gives, PD takes.
Energy needed for gives the energy to move.
EMF is the source of the energy in the circuit, and PDs are the consumers of the energy, like the resistors. An EMF of 1 volt means each coulomb of charge is given 1 joule of energy. So if there's an EMF of 1, it means each coulomb carries the potential to do 1 joule of energy. Whereas a PD of 1 volt would mean between 2 points, each coulomb has done a joule of work. So although it's voltage in both cases, we say EMF when that energy has been given to the coulomb, and we say potential difference when that energy has been taken from the coulomb and done some work, like turn a light on or whatever. So the key thing here is EMF is a voltage as well. They want this definition in the exam. Of course, you don't need all of that. It is enough, let's see, to have the first sentence. If you can have the first 2 sentences, you would guarantee full marks for the definition. Although sometimes they're not too picky in the exam, the first sentence might be enough. Please write the first and second sentence at least.
The energy provided by the cell of
No, actually it is called the seat. Is that what you're asking me, if it's a typo?
No.
What are you asking me exactly?
EMF
Yeah.
is the voltage provided by the cell for the electrons to travel through the circuit, as a definition.
It is yes.
Okay, I'll just write this.
No. I just think I might need to add 1 word in. Say it again.
The voltage provided by the cell for the electrons to travel through the circuit.
I would just love if you had the word developed in it.
Developed by the cell.
Now we're talking. You wrote the first 2 sentences down for us? Great. Please be careful. Is that dinner?
Yeah. I have party today.
You have party today? Whose party?
I don't know.
Someone's?
Yeah,
Someone.
he invited me.
Someone you know?
Yeah.
Oh good. That's a start. Oh dear. So what are you going to write on the card? Happy birthday, person. Fum Puan. Alright, continue? Yes? Okay. So basically EMF gives and PD takes. Now, this circuit here. What?
Back to memory lane.
Now, we have a battery, like say an AA battery, it'll look like this.
First you can get that.
I don't know. It doesn't matter. The maths and physics are still right. Now, you might notice when you have a battery, it gets warm after a little bit of time. So what's happening is the battery isn't perfect.
It uses up resistance.
It does. The battery has a little resistance in it. It's a bit like the battery we imagine has a perfect cell in it of voltage E, but it's also like there's a little resistor inside of it using up some of the voltage. Now I say important word here is like. It's not really like this because nobody would make a battery like this because this is wasted. I'm just saying it's like there's a perfect battery, perfect cell, and then there's a small resistor inside that slowly warms up as it uses some of the voltage. Do you get what I'm saying? So this is not the real picture of a AA battery. It's like the way we imagine it operates. Do you understand what I'm saying?
Don't
Yeah.
get a battery and cut it to see what's inside.
Yeah. You'll be disappointed. It's not like this. What we would like to know is what is this? Now, like we were saying, it's not like it's really inside the battery. It's just an imagined resistor because it's kind of like the battery's inefficiency. So because the resistor isn't really there, there's no way to measure it directly. We can't cut the battery open and take it out and measure it. So we have to have some kind of experiment to measure what is called the internal resistance. So I think, yes, we can do it that way, it's fine. I didn't write down the name of this. This is called the internal resistance. Is this here? So what we do is we connect it up to, now my diagram is, I'll do it a little bit different. We'll connect it up to a variable resistor here. We'll put an ammeter here, and usually we put the voltmeter around the battery or the resistor, but you realize it's the same. If I put the volt here or here, you get the same answer because it's only, nothing is in between these. It's like I just clip it here or here. It's the same. You might think, wait, no it's not, because this should be the voltage around the battery and this is the voltage around the resistor. But if you look at what's happening, the current leaves here, travels along here, through here, and back here. What you're looking at is the change in the voltage through the resistor. It doesn't matter if you clip the voltmeter on the top or at the bottom. Anyways, that's not really important to the diagram. I will put the voltmeter, well, I don't know, where would you like it, top or bottom?
Top.
Okay. I'll put it on the top then. So, what are the two things we can measure here? We can measure voltage and current, and what is the thing that we want? The resistance. Let's use Kirchhoff's loop rule. Oh, and the other thing we would love to know as well is what is the EMF of the battery. It'd be great if we can get both. So Kirchhoff's loop rule. Let's start here with the E and go around. So I have E minus. Any resistor? No. Here, this is an OR, which we can change. Yeah. So that's E minus I OR. Yes. And then it goes back, and then this one here is minus I small r equals 0. This is my first formula. Now actually, this here, you know what it is, because you have V equals IR. Or in other words, it's the voltage on the voltmeter. So we can change that into E minus V minus IR equals 0.
What's IR?
The voltage here in this resistor. V equals IR. It's just we have no voltmeter that can measure this. We can only measure this one. So we can't replace this with any V's. Yeah? Okay, so what is the thing that you are changing here? What are you adjusting?
Beats.
Yeah, you're adjusting the OR, but there's no OR in this formula. So as you adjust the OR, which is the thing you consider as being changed? The V or the voltage, and then you're observing the I. So the I is like the Y, and the V is like the X. So I should rearrange this. The I is like the Y, so I get E minus V equals I OR. I'll divide by OR. I get I equals E over OR minus V over OR. So I get I equals minus 1 over OR V plus E over OR. Yeah?
Yeah.
I just wrote it the other way around. Yeah? Is that okay? Yeah. So if you were to make a graph here where you put I on the y-axis and V on the x-axis, and the graph will be sloping down, doesn't go through the origin here, what would the slope of this graph be from the formula here? Minus 1 over OR. So now look, you've found a way to get the OR. The OR is going to be minus 1 over the slope. So by adjusting this to get many values of V and I, you can make a line, you can get the slope, and now you have a way to get the internal resistance. Likewise, once you know the internal resistance, you can work out the E. Because what does the C here equal?
I.
Plus E over.
E over OR. So the C equals E over OR. So the E would equal the C from the graph multiplied by the OR. But they never really ask for that. It's only the OR that you care about finding here. But I'm saying it's also possible to find the E as well. Now, there's another formula here. Yeah, you could rearrange this slightly, but it's all the same thing. No, I'll just go back in a second.
Does he affect the resistance?
It does, yeah. Now, it's a bit of a pain. Wait, before we go on, I would prefer if the I is on the y-axis and the V is on the x-axis, because then you get the proper graph. The V is what you change and the I is on the y. But sometimes in the exam, they ask you to make the graph the other way around. They ask you to put the I here and the V here, the other way around. So if the graph was the other way around, the formula, we'd have to rewrite it. We need to get V, well, it's kind of a bit easier. V equals minus or I plus E. So in that case, the graph is still going down. This time though, what does the slope equal? Minus or. So then or would equal minus the slope. Now I think the reason we use the graph this way is because it makes it easier to find the E. Because what would the E equal here?
The V intersect.
The V intersect here, yeah. So I should say the E equals the intercept. The reason I'm doing both possibilities is because, in my opinion, both are fine. I actually kind of prefer the first one because you're putting the variable on the x-axis, which is more usual. But in the last time this came up in the exam, they asked you to draw the graph so that V is on the y and I is on the x. Now, I don't actually know if that was a typing mistake and the person writing the exam meant to say it the other way around. So it doesn't really matter. The key thing is, once you have this formula, you either write it so that it's V equals, or you write it so that it's I equals. And then you can see what you need to do to get the OR. Okay, so this is the key formula here. But how did we find this key formula? We used our pal,
Kirchhoff.
which rule? Loop rule. Okay, so please note these three formulas and try to have the arrows for the two possibilities. And then if you go with this possibility, you have this result. And if you go with this, let me just write numbers here. This is 1 and this is 2. So if you go 1, you would have this formula. And if you go 2, you would have this formula. You got that? Okay. Continue.
The E
Yeah.
and IV
Yeah.
is still the intercept.
In which one?
And your graph.
The first or second?
The first.
The E is not the intercept.
But it's still the C.
You still need to use it. But
No. The intercept with the I.
yeah, gives you E over R.
Because I'm writing,
Yeah.
if I write V equals E minus IR.
Yeah, which is the case
and draw,
2.
And draw this graph.
Yeah.
This is wrong. This graph is wrong.
Yes, because V is the Y, the subject. The V should be on the Y-axis and the I should be on the
So
X.
the subject should always be on the Y.
Oh yes. Yes. Okay, continue. So look, there's only one example to do and then we'll finish. We need to make the graph here. So, tell me, which graph will we go for since it's given us a choice? Do we want to go with the first or the second?
VI.
I mean to say, should we go for, look, situation 1 where we make I the subject, or situation 2 where we make V the subject? Yeah, because it gives us easier formulas here for calculating the OR. So just write down this table, and then we'll plot it, and then we'll calculate the OR and the E.
So, Stephen,
Yeah.
makes resistance increase.
What's that?
As the temperature gets higher, the resistance increases. Is that why phones get so hot?
No, what's happening is the phone has a small the battery has a small resistor inside it,
Yeah.
effectively. And small resistors are doing some kind of work. So this small resistor is doing work you don't want it to do. It's heating up the battery.
Yeah.
So what's happening is, as the battery is on and the current is running through the resistor, it's producing heat. If your phone has no way to let the heat out, you know, like if it's in your pocket or whatever, then the heat just builds up and it gets warmer and warmer. So it's just the heat collecting up in the battery.
Okay, why does it switch off when I'm here, like in the cold weather? Like it used to switch off sometimes. Like when
Batteries can be affected by the temperature. If batteries get too cold, it's a chemical thing, you know. Batteries are chemical. If they get too cold, they start losing their charge. So like if you leave a battery in a cold room for a few weeks, you might discover that when you try to use it, it's dead. Okay.
Because I thought that would only happen if the weather was like hot.
What?
Like, cause my phone has been switching off lately. Like, it
What
doesn't
phone do you use?
And you find also as well, when you're talking to people, the call hangs up. The call disconnects when you call people.
That's not the battery.
No, you call someone, you say hello, and then the call drops.
The phone just switches off at like 50%,
Yeah.
50% battery just switches off, and then I'd have to like kind of keep it warm. And then it's an iPhone.
Yeah, that's the problem, I think.
No, iPhone is
Yeah,
really good.
because you know the Samsung phones get really hot. So hot actually they can.
They explode. Exactly.
Take that, Samsung. Okay, do we have this table written down? Right. So, come on. Okay, so we've decided we'll go with current and voltage. Yes? Okay. So, please give me the current. Let me just open up a spreadsheet here. And we'll go. What's the... come on.
1 to 0.1.
It's going down in 0.1s. Right, so current in amps starting at 1 and decreasing by 0.1 each time until we get to 0.1, and then what's happening with the voltage, the potential difference in volts?
1 to 1.9
Increasing by 0.1, huh? Okay, and let's plot this. So what's the name of the plot?
9.
Scatter.
9.
No, scatter. And then this is voltage, potential difference versus current. X-axis is current in amps and the y-axis is potential difference in volts. And here's the graph. What does the slope represent here? Minus R. So let's calculate the slope. We'll go with y2 minus y1 over x2 minus x1. Okay, so if I take out the calculator here, right, what will we go with? It says it here, 1.9. 1.9 minus...
Isn't it y2 minus y1?
Yeah, it doesn't matter which way around. Over x2, which is 0.1, minus x1, which is 1. So we get minus 1. So the internal resistance is 1. That's fine. So we have R equals 1 ohms. And now to get the E, do you remember what the EMF is on the graph?
The intercept.
Where it crosses the y-axis. Now, please look very carefully. My graph stops here, so what do I need to do? Continue it, extend it back.
Yeah.
So, if I continue it back, will we say it hits 2? Yeah.
No, higher than 2.
No, if it's 0.
No problem, because the program can give me the formula exactly. Show equation. So, the 1 is the R and the E is 2. So this is actually a good question to get if you do get in the exam. All you do, draw the graph, measure the slope, measure the intercept, and you have your E and your R. And that's it. That's all there is to it.
How to measure
The E is where it crosses the y-axis.
Yeah, but how to calculate?
You need to draw it on graph paper and measure it. You don't calculate it. Yeah.
Or you can
Use Excel.
make an equation for the line with the points.
You could do that, yeah. Okay, this is your homework, just the one question. I want you to make a graph, and there's some things to answer about it. So this is for... There's homework to do on the last lesson, but I'm not going to do it next week because the only one that was a problem I did. I'll do this one next Monday? Tuesday. And then there's one more electricity lesson, and then we're on to the final chapter then.
Untitled Chapter for semester 1 here.
Yes.
This is the